Hello students, in this video we'll discuss the almost sure convergence of our definition of Brownian motion. Let's recall that xc0, xc1, xcn, etc. are IID, normal, 0, 1, and we define Brownian motion as our random Fourier series as xc0t over square root of pi, no problem there, plus 2 over pi square rooted, the sum, n goes from 1 to infinity, and then xcn, and then the sine of nt over n, right? And so I need to show that this series converges almost surely, and then later we'll show that it converges almost surely to a continuous function. Great. And so what's the idea? The idea is that if I look at these individual terms over here, if I call these terms over here zn, right? Then of course, what's the mean of zn? Then the mean of zn, the expected value of zn, is equal to 0, obviously. And the variance of zn is just going to be the absolute value, or just sine squared, of course. So sine squared of nt over n squared, like so. And then the variance of psi n is just equal to 1, right? So of course, now the key thing here is that when I sum the variances, so I can note that the sum as n goes from 1 to infinity of the variances of Zn are less than infinity. They converge almost everywhere, right? Excellent. So I have a sum of variances. These are just real numbers though, right? So that's no problem there. And so now I need a proposition. So we're going to use the Kolmogorov maximal inequality, right? It says the following proposition. If you have, let's say, x1, xn, IID, mean 0, and bounded variance, if the sum of the variances is convergent, then the series converges almost surely. Almost surely. Great. Okay. So here's the idea. So we recall the Kolmogorov maximal inequality. So recall Kolmogorov maximal states the following. It's saying in the same setup, basically the same conditions, it says that the probability that the maximum 1 less than or equal to k less than or equal to n of sk being larger than lambda is less than or equal to what? Lambda negative 1, the variance of Sn of the last one. That's the Kolmogorov maximal inequality, and that's exactly what we're going to use here in this proof over here. So now let's estimate this. So by Kolmogorov maximal, let's just show our recall. So here's our proof of our proposition. So proposition proof. All right, so now what I'm going to do is I'm going to let Sn be the standard thing. So let Sn be just x1 up to xn, the random walk. Okay, and so now what I'm going to do is I'm going to estimate the probability that, let's look at the maximum between m capital for m and n capital of just s what? S little m minus s big M. If I go to the maximum of all those things, where that's bigger than epsilon, or bigger than or equal to, doesn't really matter. Epsilon is less than or equal by Kolmogorov maximal, epsilon to the negative 2, the sum from m plus 1, let's say k goes from m plus 1 up to n of just the variance of the terms in the sum, right? The variance of xk, right? Now, of course, what I'd like to do over here is I'd like to let n go to infinity. As n goes to infinity, this inequality remains the same. So let n go to infinity. Okay. As n goes to infinity, what does our inequality become? Our inequality becomes probability that the supremum over all m bigger than or equal to m capital of Sm minus Sm capital is less than or equal to epsilon is going to be what? Is less than or equal to epsilon to negative 2. The sum k goes from m plus 1 to infinity of just the variance of xk. Now, of course, as m goes to infinity, this goes to 0, right? So this tends to 0 as m goes to infinity. Okay? Now, the final step, I want to prove this is Cauchy, right? So I'd like to show that my sequence of partial sums is Cauchy. So to do that, what do? So now I consider omega n, let's do m actually, is just going to be the event, is what event? Is the event that the supremum over all n and little m bigger than or equal to m of s m minus s n is bigger than or equal to 2 epsilon. Then the probability of omega n, of course, as m goes to infinity, this goes to 0, right? So in other words, the probability of omega m is what? Probability of omega m is less than or equal to this probability over here, right? Because if I can just sort of fit them down to level m, so by the triangle inequality, I can fill in an m over here, saying that bigger than or equal to epsilon over 2. This is less than or equal to epsilon to negative 2. The sum k goes from m plus 1 to infinity of the variance of xk, right? And that goes to 0 as m goes to infinity, right? And so that says the probability of omega m is going to 0 as m goes to infinity, and that shows, of course, that this sequence over here is almost surely Cauchy, right? So in other words, we have an almost sure Cauchy estimate. So Sn is almost surely a Cauchy sequence by this estimate, but the fact that the probability of omega m goes to 0, and that says that our sum converges. The sum n goes from 1 to infinity of xn converges almost surely. Now, the beautiful thing is that since I get an almost sure convergence, I automatically know what? We saw in a previous video that the expected value of b of t squared was equal to t. Expected value of b of t squared was equal to t, and the expected value of b of t was equal to 0. We saw it in the previous video. And now I know the series converges almost surely. I know it converges in distribution as well. So the finite distributions of these things, if I cap up this sum over here from 1 to infinity at a finite number, I know the sum of independent normal variables with coefficients is still a normal random variable. So the distribution is the same. Since I have convergence and distribution, I know that this thing over here is going to converge to something that is in fact normal 0t. So the almost sure convergence implies convergence and distribution, and that allows me to conclude that this b of t is in fact normally distributed. Now we have the b of t is normally distributed. It converges almost surely. It converges to a normal random variable. Its covariance is correct, and the sample paths are continuous by a previous video. So that verifies that this is in fact a definition of standard Brownian motion. Thank you very much.